Chapter 3 is about what are called discrete random variables. Oops, that's not a V. There's a V. Variables. Oh, this gets to be fun. Discrete random variables. All right, let's start with a baseball example, or softball if you prefer. You know, I used to follow baseball a lot in like the 70s, 80s, and 90s. Not so much recently, but I have to say I've noticed that team batting averages seem to be a lot worse these days than they were like 10 or 20 or 30 years ago. Like, so your typical baseball player has got a lower average than they used to. It's like they're trying to hit home runs all the time. That might be part of the reason. There's like the overshifts, which I guess they've kind of done away with. Another part of the reason. Back 20, 30 years ago, the typical baseball player might have a 260 or 270 average. Now it seems to be like 230, which I don't know, just seems crazy to me. But let's go ahead and pretend we got a baseball player with a 230 average, meaning their probability of getting a hit on any given at bat is 0.230. 23% of the time, when it's an official at bat, they get a hit. Now, as was mentioned last week, if they have that average and they then get a hit in their next at bat, their average goes up. If they fail to get a hit, it goes down. If they get walked or get hit by a pitch, or if it's a sacrifice, etc., that doesn't count toward their average. But we sort of are just thinking about regular at-bats, official at-bats, they're called. And let's say this baseball player, you know, or you're told, hey, they got up 3 times during the game, which is usually they get up 4 or 5 times. Say there were 3 official at-bats in the game for this particular player. I could ask various kinds of questions. I could ask, what is the probability that this player had a really good game, say got 2 or more hits? What is the probability of getting, or I could phrase that differently. I could say 2 or more. I could also say more than 1, which would mean 2 or more in this case, because you can't get like 1.5 hits. I think I'll phrase it that way, more than 1 hit. I hope it's somewhat intuitive that with such a low average, it's not very likely that they're going to get more than 1 hit. Maybe getting 1 hit is reasonably likely. Most likely, they're probably going to get 0 hits in 3 at-bats. But certainly, they get hit sometimes. So some games, they'll get 1 hit. Maybe very rarely, they might get 2 out of 3, or even 3 out of 3 if they're really lucky that game. I could also ask other questions that are less obvious. I could also ask, over many games where this player gets 3 official at-bats, what's the average number of hits they got? I could also ask that kind of question. Over many games with 3 official at-bats, AB means at-bats. What is their average number of hits? I'm only talking about those games with 3 official at-bats. Of course, some games they're going to get 4 official at-bats, and maybe even 5 or 6, or 2 if they get taken out of the game partway through. I'm only focused on those games where they get 3 official at-bats. I could also even go deeper and say, How about not just the average number of hits? Could I also measure the average spread in the number of hits? What do I mean by that? Well, it's got a name. It's called a standard deviation of the number of hits. Standard deviation is a quantity that represents spread in a way I haven't told you yet. You know, in a sense, how consistent are they? If they're really consistent, getting almost always either 0 or 1 hit, then the standard deviation might be relatively small. If more often they get 1 hit or 2 hits, but then they also have lots of games where they get 0 hits, and they still have the same average, then the standard deviation might be bigger. Somehow this number called the standard deviation is going to represent the amount of spread, typical amount of spread, on average, you might say. Okay, so how do you figure these things out? I hope the green question here, probability of getting more than 1 hit, feels like it's probably easier. Like you maybe even could do it on your own. Let's go ahead and try to answer that first. Before we do so, I'm going to define a variable. I'm going to let capital X, which when Dr. Wetzel taught this class, I believe, memory serves me right, he almost always made that look like a Roman 10, or is that's a 5? I'm forgetting. That's a 10. That's a 10. A Roman 10. I think that's the way he made his capital X's. I typically just make them look more like a big X without bothering to make them look like a Roman 10, Roman numeral 10. Let capital X equal the number of hits in 3 at-bats. In a given game. In a given game. This is what's called a random variable. A random variable. In fact, it is a discrete random variable. As in discrete math, which I hope you know is not math, not that kind of discrete, right? They're spelled differently. It's T at the end instead of ET. This kind of discrete means, well, you could think of it as equivalent to finite or maybe countably infinite math. Some math classes are even called finite math. As opposed to calculus, which is continuous math, where X can be any real number on a continuous number line, and your functions are continuous graphs. Just dropped my pen head. This is discrete because it can only take on, in this case, a finite number of whole number values. Possible values that X can equal, typically called lowercase x. And I do try to make my lowercase x's in this course slightly cursive looking. I'm actually lazier in my other courses and don't bother. But in this course, it's so important to distinguish the capital X's from the lowercase x's that I try to make a habit of doing that. What are the possible values of the random variable capital X? Call those values lowercase x. Well, you could get 0 hits or 1 hit or 2 hits or 3 hits. 0, 1, 2, or 3. This is not real precise notation, but I hope you get the idea. Those are the possible values that capital X can take on. Can't take on decimal values that are not whole numbers like 1.5 or 1.74 or pi, or can't take on negative values, or not even negative whole number values like -1 or -2. Can't take on whole number values bigger than 3, like 4 or 5 or 6, right? Not possible for this random experiment for that to happen. Does that mean I could think of this collection of numbers as being the sample space? Yeah, you could. But it's going to be traditional to, when you write the probabilities in this context, to relate it to the variable itself. And so the question that we're trying to answer, the probability of getting more than one hit in this notation, is not just going to be P of, write it out in words, more than one hit, but I'm going to say probability that capital X is greater than 1. That's going to be the way we write the probability of getting more than one hit. That's our shorthand notation. Because, again, this random variable is discrete, only taking on whole number values, this can also be thought of as the probability that capital X is greater than or equal to 2. Since capital X is discrete with whole number values, actually, there's a little technicality here. These values that can take on in terms of the probability model are the only numbers at which the probability that X equals those is bigger than 0. We actually can and do, sometimes at least, think about the probability that X can take on other values, but the probability is just 0 in those cases. So these probabilities are the same. But what are they? What is the answer to this? Let's problem solve. Let's think about this with a tree diagram. So there's hit or not hit. In general, you want to label really with S or F. And actually with the F, maybe I should make it a cursive F. Although I'm not making my S cursive. That's very inconsistent of me. The reason I made that cursive F is because I want to reserve a non-cursive F for something different. That's still going to be used in this exact same problem. It's not that you have to make it cursive. It's just I'd like to distinguish this F from a different F. That's the first at bat. There's a 0.23 probability of success and a 0.77 probability of failure, assuming it's an official at bat. Same with the second at bat. Same with the third at bat. These paths through the tree diagram represent effectively the whole game in terms of this player's at-bats. I'm continuing to label the branches with these same probabilities. Realize that when I'm doing so, I'm making some assumptions. One assumption that I'm making is that these probabilities stay constant. That's, you might say, an overly simplistic modeling assumption, because for one thing, you're not thinking about who the pitcher is. And you're also, even if you knew the pitcher, are not thinking about what if they change pitchers during the game, which usually does happen. So we're not thinking about the pitcher here or pitchers, and we're assuming these probabilities stay constant. That's effectively what are called identical probabilities over the different trials, which represent the different at-bats. We're also assuming independence. We're not assuming that if he fails to get a hit the first time, that makes him really sad and his probability of failure goes up. So like 0.8 or something, the second at-bat, the probability of failure in the second at-bat, given failure in the first at-bat, being different than the probability of failure in the first at bat. That would be a non-independence assumption. Now, I'm not saying that assumption is wrong. I'm just saying it makes it a harder problem. We're trying to keep it simple. So we assume independence as well. When at each stage of this experiment, you have two options, effectively success or failure, those are called Bernoulli trials. Bernoulli, in honor of one of the Bernoulli brothers, trials. There's Jacob or Jacob Bernoulli, there's John or Johann Bernoulli, and there's Daniel Bernoulli, and I think Daniel is just Daniel, you know. A J in German is a Y sound. Anyway, Bernoulli trials, what this refers to is on each at bat, you have success or failure, hit or not hit. They're independent. These probabilities don't change. They're not conditional probabilities. Or you might say the conditional probabilities equal the ordinary probabilities. And in fact, they stay constant. They're identical. To find the probability of what happens during the entire game, multiply along the branches. We did this before. There was a class last week where we did this exact same kind of thing, except the batter had a 300 average. So for the probability of 3 successes, it's 0.23, not squared, but to the third power, right? 0.23 times 0.23 times 0.23, 0.01217 is what would go there. And that would be the probability of getting 3 hits and 3 at-bats. For a hitter who has a 230 average, say approximately, over the course of a season, about, well, 1.2% of their games, they're going to go 3 for 3. If they have 3% of the 1.2% of the games where they have 3 at-bats. Now, if there are some games where they have 4 official or 5 official at-bats, which will definitely occur, that happens quite often, actually. You could still think about this and just think about their first 3 official at-bats and just ignore the last 1 or 2. The 162 games in a season, if this player plays all 162 games, 1.2% of that might be like 2. 2 out of 162 games, they got 3 hits in their first 3 official at-bats. 1.2%. How about getting 1 hit in 3 at-bats? Well, or 2 hits. Let's do that one first. Getting 2 hits corresponds to, well, one way to get that is that path. A second way to get 2 hits is this path. And a third way to get 2 hits is this path here. Those are different pathways of getting 2 hits and 3 at-bats. But they all do represent x equaling 2. This is the probability that x equals 3. I have to find the sum of those 3 probabilities to find the probability that x equals 2. Oh, and then I've almost finished my problem. I just have to add those 2 answers. Yeah, multiply the numbers along the paths. This top path, 0.23 squared times 0.77 is 0.040733. And that is going to be the same product effectively for these other 2 paths. You got 2 factors of 0.23 and 1 factor of 0.77. So those other paths also get labeled with those numbers, or that number. Add those numbers together effectively, since they're all the same, multiply them by 3. Times 3, you get 0.122199. That is the probability of getting 2 hits and 3 at-bats. Out of 162 games, about 20 games, will such a player get 2 hits in their first 3 at-bats? And that now allows us to answer our question. The probability that they get more than 1 hit, which is the same as the probability of getting 2 or more hits, is the sum of these 2 probabilities. So it's 0.122199 plus 0.012167. It's 0.134366. That's the answer to our question. Out of 162 games, it's about 22 games. Realize these answers, these numbers, are probably too many significant digits. I mean, the batting average itself effectively is, 230 is only given to 3 significant digits. It's probably best to round these to 3 significant digits, so 0.134. It's not something I really worry too much about, but in reality, that's probably what you should do. But keep as many digits of accuracy as you can until the very end. They're much more likely of getting 0 hits or 1 hit. 1 hit is also represented by 3 passes through the diagram. If your diagram is getting too messy, don't bother doing the circling that I'm doing. These are the 3 paths of getting 1 hit. And to find those probabilities, I didn't emphasize it, but I'm using the multiplication rule for independent events. I'm using that here, in case that wasn't clear. I forgot to mention in doing these multiplications. In each of those paths, I've got 2 factors of 0.77 and 1 factor of 0.23. Each of those probabilities is 0.136367. Add those probabilities. I'm using axiom 3, the addition rule. Since they're all the same, it's the same effect as multiplying them by 3. Multiply by 3, we get 0.409101, which you'd run around to 0.409 for the probability of getting exactly 1 hit in 3 at-bats. For the first 3 at-bats. Out of 162 games, that's about 66 games. The last one, the last answer for the probability of getting 0 hits does have to be 1 minus the sum of these 2 things. Because that's the only other thing that can occur with non-zero probability. It's got to be 0.456533. But we should be able to confirm the answer by doing 0.77 to the 3rd power, because this last path represents 0 hits. This should be the same as 0.77 to the 3rd power. And yay, it is. Amazing. Math is consistent. 0.456533. That is the probability of getting 0 hits in the first 3 at-bats. That's going to occur in about 74 games. This is modeling, mathematical modeling at its finest, you might say. Making assumptions, not thinking about pictures. And because we're not, we're keeping things simple that way, it's not going to be perfect. And if it's at the start of a baseball season where you're making these kind of predictions, it is based on the past, and maybe now the player is better or worse. They've improved a lot in the postseason, or they've gotten worse. They've let themselves get out of shape or whatever. Okay. It's modeling. to make these kind of predictions. But I hope you see it. It's useful modeling. And it could apply to the business world too. You know, I don't know. What's the probability if maybe this probability is now not the probability of getting a hit in an official at bat, but the probability that there's an earthquake somewhere in California in the next year. Of course, there's actually small earthquakes all the time in California. So when I say that, I have to say probability of an earthquake of a certain size or more on the Richter scale, like 5 or more is considered a fairly big earthquake on the Richter scale. Maybe that's the probability of getting such an earthquake. And what you're wondering is, what is the probability of getting more than one earthquake in the next 3 years? And if you use these same kinds of assumptions, Bernoulli trials that are independent and identically distributed, you get the exact same answers. Earthquakes, thinking about them is useful for insurance companies, right? Because they got to pay out money to people based on damages. So they want to know these kind of things. They want to develop models for these kinds of things so they know how much to charge their customers. When you pay the insurance company, it's called a premium. What should the premiums be so that the insurance company can both pay off the claims from the damage and also still make money, still stay in business? They don't want to run out of money. That would be a bad thing. You know, people complain about working with insurance companies, but it's understandable. There are conflicts of interest. They're trying to stay in business. You're trying to get covered. There are conflicts of interest that are going on. If you want better coverage, so to speak, that is more likely to cover you when you have damages, you probably have to pay bigger premiums. You get what you pay for. That's the way it works. Okay, so there are lots of real life things to think about here that you can apply this to. For our last half hour, we need to focus on some other things related to this that are really, really important. Okay, so make sure you're really paying good attention. I now want to address these other questions. Over many years with games with 3 official at-bats, what's the average number of hits? What's the standard deviation number of hits? Center and spread in statistics is the way you think about those. To simplify things, I am going to take these numbers and effectively round to 3 decimal places. I still want the sum of the numbers to be 1, so hopefully that'll happen here. And I'm also going to introduce an important new notation using the letter F, like I mentioned. I'm going to let F of lowercase x be the probability that capital X equals lowercase x. And yes, you are seeing 2 equal signs here, but realize there's only 2 quantities that are equal to each other. This quantity and this quantity. The equal sign inside there is more like an abstract idea. I'm wondering what happens when capital X equals little x. Random variables themselves are kind of abstract ideas. The capital letters are abstract ideas, you might say. But then for a particular experiment, like a particular baseball game, they take on a particular value. You call that little x. It's a little confusing. And based on this definition, I'm going to create a table of values for little f of x. Could make the table vertically, but the book tends to make it sideways here for the sake of typesetting. The values that capital X can take on with non-zero probability in this context, again, are 0, 1, 2, and 3. Again, I could make this table vertical as well. And again, I'm going to take the numbers from before and I'm going to round them. The probability of getting 3 hits and 3 at-bats, I'm going to round to 0.012. The probability of getting 2 hits and 3 at-bats, looking at my numbers from the previous page, I'm going to round to 0.122. of getting one hit in 3 at-bats, 0.409. Now, because of rounding, I'm not sure that what I put here is going to match what I found on the previous page. If I add these numbers up, 0.409 plus 0.122 plus 0.012, and then subtract that from 1, I get 0.457. Fortunately, that is what the previous answer does round to. Okay, previous answer for x being 0 was 0.456533, and oh yeah, just barely it rounds to 0.457. Okay, that wasn't guaranteed to happen. If it didn't happen, if this rounded to 0.456, I'd still put a 0.457 there for the purpose of making these add to 1. Or yeah, okay. So it's a little funny that way. What I'd like to do now is again find the theoretical average number of hits in 3 at-bats over many, many games with 3 at-bats. That's called the expected value of x. It's got some special notations. The first notation that I'm going to use is a Greek letter. That's the Greek letter mu. And I love that that is the Greek letter mu, because it kind of looks like an M and it kind of looks like a U. Mu. I guess the other possibility is but mu is what it is. That is the standard symbol in probability and statistics for a mean. And oh, isn't that fortunate? Both mean and mu start with M. It's also called an expected value and written this way. Expected value of x. I do like using square brackets here. There's nothing wrong with using parentheses. Though, you know, I've been using parentheses all along with these kinds of symbols, whereas the book uses square brackets. You probably noticed. It's not a big deal. And again, it wouldn't be a big deal if I use parentheses here. And if you want to, you certainly can. But it's force of habit. I like using square brackets here because that's what Dr. Wetzel did. I'm using notation consistent with him, although I'm not making my x's look like Roman numeral 10s. The mean, mu, and the expected value x are the exact same thing. They're different symbols, different terms for the exact same idea. And what is it? It's a theoretical long-run average. That's what it is. Well, how do you find it? Here's one way, but this way I'm about to show you is not the main way you will do it. You could pretend, for the sake of pretending, since there's 3 digits of significant digits in each of these numbers, that the player gets up, the player plays 1,000 games in its career and gets at least 3 official at-bats in all those 1,000 games. In how many games, if that 230 average is consistent through their entire career, in how many of those 1,000 games would you expect that they get 0 hits? Oh, 0.457 times 1,000. There's going to be 457 zeros in this average. What's an average? You've done this since what? 5th grade? Take a bunch of numbers, add them up, and divide by the number of numbers, right? That's the average. Mean. There's going to be 457 zeros is what this means. There's going to be 409 ones. There's going to be 122 twos and 12 threes. In 1,000 games, there were 12 games where you got to hit 3 out of the first 3 at-bats. Over how many games? 1,000. This is like taking 457 zeros, adding them up, adding on another 409 ones, adding on another 122 twos, and adding on another 12 threes, and then dividing by the number of games, 1,000. Now, is this really what happened with this player? No. In all likelihood, no. But if you don't have any other information other than his batting average and how many games he played, 1,000, this would be your best guess for the average number of hits in the first 3 at-bats. What is it equal? Well, do the calculation. 0 plus 409 plus 366 plus 36 divided by 1,000. 409 plus 366 plus 36.
That should be 244.
What should be two? Oh, I thought it was times 3. Thank you. 244. 409 plus 244 plus 36 is 689 divided by 1,000. 0.689. That number is not a probability, even though it's between 0 and 1. It's the average number of hits in the first 3 at-bats in all 1,000 games. If he was a much better hitter, like better than 333, 0.333, like at least 0.334 for his probability of hit, this number would have been bigger than 1. But that would have been okay because it's not a probability. The units for this would be hits. Not a probability. There's another way this could be computed, which is actually going to be the more common way we do it. We could take this fraction and seemingly for no reason break it into pieces in the following way. We could write it as 0 times 457 over 1,000 plus 1 times 409 over 1,000 plus 2 times 122 over 1,000 plus 3 times 12 over 1,000. And those fractions over 1,000 could also be written as decimals: 0.457, 0.409, 0.122, and 0.012. And in the end, you'd get the exact same answer. This second way is actually the better way of doing it because it's only using the given information in this table. It's not assuming we get up 1,000, we have 1,000 games. Because in all likelihood, there was not 1,000 games. I mean, I just did that as pretend. Uses just the end of this information, doesn't assume 1,000 games, but does give you the same answer. You should double check. And this is going to be the more general formula. Effectively, this is a summation. In this case, x going from 0 to 3 of x times f of x. The x values are the 0, 1, 2, and 3. The f of x values are from the table. I forgot to say something very important that I should have said back up here. If you're still writing this, I'll give you a second to rewrite that if you haven't written this yet. That's a summation sign. X goes from 0 to 3. First it has a value of 0, then 1, then 2, then 3. It matches this written out summation. Something I forgot to say here. Our book calls this f of x function a PDF for probability density function. However, I even cringe in saying this. This is a place where I differ from Dr. Wetzel. He stayed consistent with the book and calling it a PDF. But I much prefer, I'll say or here, better to call it a PMF for probability mass function. Though truth be told, some people just call it a PF for probability function. PDF is the book. That's what it's called in the book. Probability density function is what it's called in the book. I, in chapter 3, will call it a PMF, probability mass function. Actually, in chapter 4, it's going to be called a PDF, and I will call it a PDF in chapter 4 with continuous random variables. But with discrete, it's better to call it a probability mass function. Why? Maybe it's best to wait for chapter 4. I will try to typically call it a PMF, probability mass function, even though the book calls it a PDF. It's more consistent with what people do nowadays. You know, our book is 20 years old. And I think it's better to call it a probability mass function for reasons I'll get into when we get to chapter 4. But there's the formula for the mean. In general, the mean, the expected value of x, is the sum, always such a sum, over, well, in general, we don't know what values f of x takes on with positive probability. So for a shorthand, we just say all x here. But that could be confusing because you might wonder, well, could x be a non-integer, a non-whole number like 1.5 or 2.7 or something? Oh no, we just got disconnected. This seems problematic because, again, it doesn't specify what x is. It's really all x for which f of x is positive, is what it means. But that could include other non-whole numbers. It could, in some circumstances, and still be a discrete random variable. It also could include infinitely many possible numbers. It could be a countably infinite list of values of x where f of x is positive, and this could be an infinite sum, like a series in calculus 2. And that does happen in chapter 3. In fact, I'm going to talk about it still today, even though we only have 13 minutes. What about the measure of spread? Well, that's called the standard deviation. But before we talk about the standard deviation, we need to talk something about else, something called the variance of x. And for some reason, we use parentheses here instead of square brackets. Var x stands for the variance of x. It's going to be a measure of spread. It's also going to be an expected value, but not of x, but something different. Of x minus mu quantity squared. Whoa, what's that? You got this random variable x. It can take on a certain number of values. In this, our example of 0, 1, and 2, and 3 with positive probability. We've found the mean. The mean is 0.689. That's mu. That could be plugged in there as a number. We might wonder over many, many games with 3 at-bats, if you take the number of hits and subtract the mean and square it, what's the long-run average of that? First of all, realize it can't be a negative number because we're squaring it. There's no imaginary numbers in this course. So this can't be negative. This has got to be a positive quantity. What does it equal? How do you compute it? You do another summation over all x, for which f of x is positive. A summation that looks like this. Take the possible values of x, subtract the mean, square it, multiply by f of x. For our example, that would look like this. 0 minus 0.689 squared times 0.457 was f of 0. 0.689, that's the mean. This is the baseball example. Plus 1 minus 0.689 squared times f of 1, which is 0.409. plus 2 minus 0.689 squared times 0.122. 0.122 was f of 2 plus 3 times 0.689 squared times 0.012. That was f of 3. Whatever that number turns out to be, I'm not going to take the time to compute it. It's called the variance. It will be a positive number. The variance has another symbol, sigma squared, lowercase sigma squared. Huh? What are we squaring? Well, you might say we're squaring that, but we're not squaring the entire answer. So why is it called sigma squared? It's called sigma squared because it's square root. The square root of sigma squared, the square root of the variance, is called the standard deviation. And that's the better thing to use to measure spread for the purposes of understanding. The variance is actually better as a measure of spread for theoretical reasons because you don't have to deal with square roots. But for the purposes of intuitive understanding and relationships to statistics, the standard deviation, the square root of the variance, is better. Something else I should say here is that this formula that you see here is actually not the way we typically compute the variance. It's the definition of the variance, but the way we compute the variance is different. It's a theorem that's fairly easy to prove that the variance also equals the expected value of x squared minus the expected value of x squared. Oh, these are different. That's the expected value of the random variable x squared, which turns out to equal this summation. But this thing, or this entire thing, is mu squared. And it's different. These are not going to be equal unless your random variable only takes on one possible value with positive probability. These are not equal. Where mu, again, is this sum. That's called the computational formula for the variance. And it's almost always what you use to compute the variance. Have I done the other method? Yes, I have, for the purposes of illustration in class. But almost always people use this. This certainly was much better before calculators and computers came along to do it this way. Because you didn't have to deal with a mean that was some crazy decimal like 0.689. That's why. Well, okay, you did have to deal with it, but it was in just one spot instead of a bunch of spots. It's a theorem. It takes proof to prove it. The proof's not hard if you know properties of expected values, which I should now mention those. We got 2 more things left to do in 6 minutes here. 6 minutes here. Properties of expected values. First property being that the expected value of a constant is 0. That's a constant. No, excuse me. Is the constant itself. Sorry, I was thinking of variance. The expected value of a constant is the constant itself, a constant random variable. This random variable is a constant random variable, means it takes on only one possible value with positive probability, the value c. Secondly, the expected value of x plus y equals the expected value of x plus the expected value of y. Actually, I might be getting the order of these wrong. The third property is that constants can be pulled out in front. I think the book maybe switches these around. Swapped in the book. Okay. Think about the second one here, which I think is the third one in the book. Pretend X is your average, your bowling score, and Y is my bowling score the next time we decide to go bowling together. And we're wondering if we go bowling together many times and add up our scores, on average, what is our combined score going to be? This would be what that represents. I hope it's pretty intuitive that it should be my average plus your average. That seems pretty intuitive. Actually, proving this is much harder than the intuition would imply. Because X and Y, these two random variables, notice the capital letters, would have different PMFs, different probability mass functions that could be positive over different domains. And so it gets kind of tricky to actually prove this. We need ideas from chapter 5, actually, but it's fairly intuitive. And that is an example of one property you need to verify this. Actually, properties 2 and 3 can be combined into a fourth property. To say the expected value of a linear combination like this, AX plus BY, where A and B are constants, is this kind of linear combination. And you can even extend it to the sum of more than 2 random variables here. E, the expected value, is an operator, kind of like a derivative operator. DDX, derivative operators have similar properties. These are called linearity properties. Final thing I want to mention that will come up on your homework in the last 3 minutes is a particular other kind of random variable. The main random variable we focused on here, number of hits at 3 at-bats, is called a binomial random variable. Binomial. This final random variable for today is called geometric. A geometric random variable, which can come up in the baseball example. Same probability of success on any given at bat, 0.230, say. But X, the random variable, is going to be something different. It's going to be the number of at-bats until the first hit in this game, or maybe over many games, because maybe he doesn't get a hit in this first game, and maybe doesn't even get a hit in the second game. It's not until the third game that he gets a hit. Counting official at-bats until the first hit, and then stop. So X is not the number of hits in a certain number of at-bats. It's the number of at-bats until the first hit. P is the probability of success on any given at-bat. We're going to let Q be the probability of failure, 1 minus P, on any given at-bat. And it turns out the probability mass function in this context, f of little x, the probability that capital X equals little x, is P times Q to the x minus 1 power. This can be derived by thinking about a tree diagram very quickly. It turns out to be an infinite tree diagram that looks like this: success, failure, success, failure, success, failure, success, failure, etc. You stop when you get the first success. You got a 0.23 probability of success on any given at bat and a 0.77 probability of failure, etc. By thinking about this tree diagram, it leads to this formula. This formula is valid for infinitely many values of X, 1, 2, 3, 4, etc. Capital X is still a discrete random variable, but now it can take on more than finitely many values with positive probability. Infinitely many values, though this is a countable infinity. It's not like a continuum of real numbers. So it's still the discrete case. The summations that you need to compute for probabilities and expected values in this context are infinite sums. And it's called a geometric random variable for a big reason, because you need the formula for the sum of a geometric series, calculus 2. Make sure you read the section about geometric random variables very carefully. One other subject is going to come up that I didn't get to, called the moment generating function. Moment generating function. I'm not going to give you, well, I'm not guaranteeing that I'm giving you any problems about moment generating functions, but if I do, they'll be fairly basic. Kind of a hard concept. Okay. All right. Have a good day.